All right, cool. So yeah, like I was saying, this module, like module 5, is going to be a lot of machine learning algorithms. So I would say this is like the big meat of like, okay, you guys have the basics of like how to use Python, exploring data, kind of cleaning stuff, and then you're going down to the like modeling aspect. And so we've already seen a few ways to model data. So we've seen like the very first one was linear regression, right? And then we have logistic regression, which is basically linear regression, but modified it so we can do classification. So if you remember that, probably what, mod 3, I think? Maybe it's even mod, no, I think it's mod 4. And then we had time series, right? So that's kind of like the 3 biggest one. We also had naive Bayes, which I think that was a really brief one, so I don't know if anyone really remembers that one, but this module is going to be kind of going through a whole bunch of things. Like today we'll go over K nearest neighbors, or KNNs. We'll go over later this week decision trees, ensemble methods like random forests, and then eventually we'll go into support vector machines. So we're basically touching all these different parts of supervised and unsupervised learning. Okay. So I think this is kind of like, I don't know, this kind of gets me excited because I'm like, cool, this is like the real big like modeling section and everything. What is nice though is that once you understand like the basics of modeling, it doesn't really matter in the sense of like what model you're going to be using for, I shouldn't say it doesn't matter, but like they're all very similar in the way you approach them, and that you need to process the data, model it, and basically you kind of come down to, well, we'll focus on 2 main different model problems. One is our supervised learning, right, and our unsupervised learning. So just kind of quick review. Does anyone remember what supervised learning means? Like what we say like when we're doing supervised learning.
Supervised, like where you train the data, and so this is a cat, this is a dog, and then you run the model given that training data. Unsupervised, you more just run it and let the machine work out a category.
Yeah, that's pretty much it. Thank you, Andrew. Yeah, so supervised and unsupervised learning, basically supervised means that you have examples of saying, like Andrew said, this is a dog, this is a cat, if you're just trying to figure out if this picture was a dog or a cat. An unsupervised learning is a little more subtle, where it's like you're not really sure, like what, you don't have examples of what the class is, or like, what is this example? So some of these things can be, for example, trying to find like outliers, or finding like, let's say if you're a bank and you're seeing a bunch of transactions from people, trying to identify what things are like out of the ordinary, which might suggest fraud or something like that, or someone stole the credit card or whatever. That would be an unsupervised learning problem. There's also things like, we'll talk more about that throughout the week. There's kind of like 2 other ones that kind of like, I almost like don't even like to mention one of them. One's called the semi-supervised learning, which I don't even like to call it that way, because basically it just means like, oh, like it's unsupervised learning, but you have some examples. So it's really a supervised learning, but sometimes people call it semi-supervised. So just kind of know like that's out there. And the last one's reinforcement learning, which actually we won't talk about in the curriculum here, because reinforcement learning is a totally different kind of beast. I think Matt Spar, right, had done a couple, or he had done in the past one of the study groups on reinforcement learning. And I think he's planning to do that again in the future. So whenever that comes up, if he plans around that, come check that out. But that's kind of like the other like learning, what's it called, like machine learning problem. But that's a very different kind of thing. So the main things we're going to focus on is supervised and unsupervised, which are going to be like 95% of all problems that you ever do. Okay. So I will go ahead and start sharing my screen. And as I share my screen, just remember that this stuff, you can find it on the repo I have online. And I'll kind of just show you guys briefly since we're on a new module, right? So what is my thing called? Repo. So you can see here is that we will be living basically within here for the next, module, machine learning. And so you can see how all these different machine learning techniques, we will specifically look at K nearest neighbors today, so KNN. So no, that's where you can find the stuff. If you guys have, what's it called, forked this repo before, just know you might need to refresh it, basically pull some information, because I do update these for, every once in a while. So if you had pulled this, let's say 2 months ago, some of this stuff might be a little bit different. So just kind of know if you are following along, you can do it that way. Okay. So, all right. So K nearest neighbors. The first thing we have to do basically is kind of define how we're going to measure something called similarity. So the idea here for k-nearest neighbors, which we'll talk about in 1 second, but is that you basically have a bunch of data points with a bunch of features. And you want to say, okay, based on that, this is labeled, let's say class A, and this is class B, and this is class C, based on what's near it, and I'll define what near is in a second, but basically what other data points are near it, that should be that they're all similar together. So the idea here is that if you have, and this is going to be really abstract, so kind of bear with me, but if you basically have a bunch of green points like this over here, you expect all the green points to be relatively close together versus, let's say you have something like some pink points over here, and pink tends to be maybe like over on this side over here. So you basically expect that these different classes tend to stay together. And this is what we mean by something that's very similar to each other. So you can kind of imagine us eventually drawing kind of like lines around this and saying, okay, this is all the pink stuff. And then if I had a green line here, this is all the green guys over here. And you can do this for multiple different classes. So you can imagine not just green and pink, but maybe something like, hopefully no one's colorblind because I think these are kind of similar to each other. But you also have blue. And so you might have a different class right here. So the idea here is that for k-nearest neighbors, basically is that similar or same classes have similar properties, so they tend to hang out with each other. Okay, and this actually turns out to be pretty true too. It turns out there's a few ways we can kind of like make this happen too, is that if 2 dimensions isn't enough, we can actually extend it out to 3, 4, 5, however many dimensions we have of many features. And we tend to have things that kind of stick around there. We can always draw kind of like essentially a bubble around the different classes. Okay, so that's what what we're gonna do with k-nearest neighbors. Real quick, if I keep saying k-means, I'm so sorry. That's a different algorithm. So just know if I ever say k-means in this context, I'm talking about k-nearest neighbors. Okay, but the first thing we need to do is figure out like how are they similar to each other. So we basically come up with something called distance. And you're gonna like kind of, I think at this point you're like, well, of course, like that's really easy, right? Like these are clearly close together versus like these are kind of closer together. But it gets more subtle when we get into higher and higher dimensions. So we have a few ways to kind of measure this. And this is similar to if you go through the curriculum, this is kind of like what the curriculum talks about, kind of summarized. So distance metrics. So basically it's a way to describe how close something is. So there we go, proxy. So just basically saying how close something is kind of a same thing as saying how similar something is. So if something's relatively close on the space of all features, it should be similar to each other. And hopefully that kind of makes sense, is that like if you had something like let's say age is one of your dimensions, right? So you can imagine there's age right here, and I guess I could just draw right here. But if you have something like age is in this direction right here, and these are all people, and then let's say, I don't know, what's an aspect? Height, okay? Height right here. And then you can even imagine other attributes like weight or likes, I don't know, likes Pokemon or something. That could be a feature too, right? It doesn't matter what kind of features are. But the point is that basically the idea here is that when we're grouping people, it's just like, oh, this is their age. Well, if they're a certain age and they're a certain height, they tend to kind of be grouped together. And these might have similar kind of like, what's it called, needs, or make sense to kind of group them together. So if I say, oh, these are people who, I don't know, I'm trying to think of something who really like burritos or something like that. It's like, oh, like all these people tend to like burritos. And of course, height and age are probably a pretty superficial like feature, but you can imagine multiple features. They don't have to necessarily be, these kind of things. But the idea here is that all these groups right here tend to be very close together. Okay, so how do we measure this closeness? So basically there's a few ways, right? Now, the simplest, like if I told like probably like a second grader, right, and said, all right, which one's closer, this one, or let's say I have like a little star right here, and say which one's closer, they would probably say, well, this one's closer, right? And they'd be right? But as we get into higher dimensions, we'll kind of talk about like, well, how do you kind of deal with that? So we have a few definitions of this, and we'll eventually get into a Minkowski distance, which sounds like a really scary word, but it's kind of like if you follow around with Manhattan distance and Euclidean distance, which is Euclidean distance is probably what you already know, it won't be too difficult. So Manhattan distance. So basically, I like to imagine this like if you're like in like a city like New York, or like a city that tends to have like, nice square blocks. a lot of modern cities now tend to be a little more curvy and stuff like that. But if you imagine like these nice straight blocks and everything like that, Manhattan's distance is basically how long it takes you to go down the blocks to get to point A to point B. So if you imagine this is point A, this is point B, you basically have to go like 1, 2, 3, 4, 5, 6 blocks up, and then 1, 2, 3, 4, 5, 6 blocks to the right. Sorry, thought there was something. So you can imagine going a total of 12 distance, right? Note that this is the same actually if you take 1 block up, then to the left, up, left, up, left. If you count it out each time you down the blocks like this will always end up to being 12, as long as you're sticking on this kind of like grid system, okay? And that's what we call the Manhattan distance. So that's kind of like the simplest way. Essentially, you just kind of count on like your steps, right? Like, you know, how long it takes you to walk somewhere. Note that this green line right here is representing, this would obviously not be a path that you can take. You can't go through a block like this. This might be like, you know, what's the phrase? As far as like the crow flies, or on the crow fly, or as far as the crow flies, something like that, right? I don't know idioms, but basically, as the crow flies, thank you. Something about crows and flying. So I don't know why it's a crow. Anyway, from point A to point B, that would be a different distance. So you can imagine that this is going to be actually shorter than doing a Manhattan distance. But Manhattan distance is a really relatively simple one. You can imagine like one-dimensional. This is also kind of called, I'm going to give you guys some terms that will come up with, oh, we've seen regularization, right? Before regularization with L1 norms, L2 norms. Maybe not. Anyway, regularization, we'll talk about it again if we haven't talked about it yet. This is basically your L1 and L2, or this is your L1 norm. So essentially this is saying the absolute value between different points from here to here. Okay, so going off of that, basically it's your formula. So basically your distance from A to B is the sum from the A, you can imagine this K being the dimension. So you can imagine this is 2 dimensions here, right? So it'd be K equals 1 to 2. And basically the distance from for A to B, which is going to be in this direction, which is 6, okay, plus the distance from A to B in this direction, which is also 6, okay? Doesn't have to be exactly 6, but then you add those together, you get a total distance of 12, okay? So essentially we're using this absolute value here, okay? Does everyone understand kind of traveling along this grid, like how we get these numbers, right? Okay, cool, I see some nods, awesome. Okay, and all we're doing here in this mathematics is basically just formalizing it into something that we can kind of like say out loud, right? Okay, so note that we can do Minkowski distance not just for 2 dimensions, but we can also do it for 3 dimensions, right? So you can see here I have points A and B, okay? And points A and B, this is in 3 dimensions, so you imagine X, Y, Z. If I kind of, we'll see how good my drawing is real quick to help visualize this. This is where I wish I was a much skilled drawer. But here's my coordinate system, right? So this is my Z axis. Let's call this my X axis. This is my Y axis. So if I do this like in 3 dimensions, it look kind of like this, right? So like they're all pointing in different directions. 2, 3, 5 would be somewhere like, if I could draw this right, I don't know, something like that. I think that looks similar to like what I'm doing. You'd imagine like over here. So like you'd imagine like this is A right here. So kind of all in the positive, and you can see here, X is going to be positive, but then negative Y, so it'd be over here, and then positive Z3, so it'd be like over here. This would be B. And what we want to know is how far A and B are from each other. And instead of just using like as the crow flies, which would be like this line straight to A to B, we basically say, okay, how far is it on the Y axis, which would be like this? How far is it on the Z axis, which is like this? I'm trying to imagine this in 3 dimensions. And then how far is it from in the X axis, which would be like, trying to make this so it's not too hard. So you can kind of imagine that you basically say, how far is it in this direction? How far is it in this direction, which is that Y, and how far is it in the Z direction? And then you add those all together. Does that make sense? Hopefully my pictures aren't too confusing in this way. All right, so what you do is mathematically now is like, okay, we can go ahead and make these little points. This is A, B, and C. So these are different vectors or different points, right? So just know you can kind of interchange points and vectors right now, because essentially if we just drew a line from here or an arrow from here, the center, the origin, to B, that would be a vector. But we could just think of them as points as well, okay? So I have these parts, and all I'm going to do is calculate the differences. Since I'm using a numpy array, I can just do a minus b, which should just do 2 minus 1, 3 minus 1, and 5 minus 3. Okay, so we should get 1, what's that, 4, and 2, right? So if I get that right, 1, 4, 2. Cool. Okay, and so that basically is representing the distance in the x direction, distance in the y direction, and distance in the z direction. Note that these all came out positive, but in order to make sure we don't really care about if it's above or below, we just want to say how far away it is, we're just going to take the absolute value, right? So if you say something is like 4 miles away or minus 4 miles away, it's the same distance, right? We don't really care about this positive or negative. That's why we take the absolute value. So we take the absolute value of this, which in this case is just 1, 4, 2. Okay. And then the last part, we basically add up these parts. So we're just going to add up 1 plus 4 plus 2, which again is the same thing as just adding up this distance, and this distance. Okay. Make sense so far? Okay, cool. So I run this guy, and that we should do 1, 4, 2, so that should be 7. So our our Manhattan distance is 7. This is also called, like I said, our L1 norm. So that is our distance here. Okay. Any questions on any part of this?
I have one.
Mm-hmm.
So does it matter, like, because at least with this example, if you just add up all the elements of A, and then you add up all the elements of B, and then you calculate the difference, it's also 7, right? Does it matter which order you do it?
I think, are you saying like, well, let me make sure I got this right. So you're saying like, if you just add up all the elements in here, so 2 plus 3 plus 5, which is what, 5, 10, right? And then add up all these guys, which is ends up 3, 7. Yeah, that's a good point. I don't believe that will work. Let me try to think real quick. Okay, no, I think that does work in general, because if you look at this, all right, who's ready for some math today? Okay, it's Tuesday. You guys are all ready for math. So if we have something like, you know, let's say A1 minus B1, I only use 2 dimensions, plus absolute value of A2 minus B2, right? Okay, that's the same. That might be the same thing as saying, well, what Giovanna was saying is like, okay, we just take A1 plus A2, get rid of this guy, and then minus B1 plus B2, right? And so one thing to kind of note there is that it might not work because it just happened to be in a positive direction here. But let's see here. If we have this guy and this guy right here, you can see that this is what we actually want, right? And we want to see, are these two equal to each other? This might not work by itself, because if B is actually larger, let's see here. I guess if we take the absolute value afterwards, we would always get A1 minus B1 plus oh yeah, I think this might not work, A2 minus B2, and then take the absolute value. And the reason why is that, imagine that this one right here is like, let's say A1 is bigger than B1, but in this case, A2 is less than B2. You might actually get in the point where these would cancel each other out because they're pointing in different directions, but they're actually, they should be counted by itself. So imagine this is like -7, and this is like +7. The Manhattan distance would be 7 plus 7, because we take the absolute value, which would mean 14. But in this case, if it was like this would actually give us 0, which wouldn't be the same thing. So you still have to do in this order, essentially. Good question, though. It does. I think in this case, like you said, it does work out. We just kind of got a little lucky. I think it's because in this case, they work each way. If you look at maybe, let's see if I can change this up real quick. Oops, minus, and this is plus. So now this will be -2 here. I think it won't come out to the same thing. So it should still add up to, let's see here, 2 minus 3 is -1, plus 5 is, where am I at? -1, so 4. And then this would be 5. So it should be, you know, let's say 4 minus 5, right? So it should be a distance of 1. But I don't believe it ends up being that. So you see it ends up still being 7, because it's just looking at the distance between here and here. Make sense? Okay. Good question though, because, you know, it does seem like, oh, maybe you could just do that. All right. Awesome. Any other questions? I want to make sure you guys ask questions here because we're about to get into a little more fun with extra exponents and stuff. Okay, cool. So think of Manhattan, the Manhattan distance, Manhattan like New York, because all of the streets in New York are all nice and straight. So it's like walking down the blocks. I just came up with that right now. Okay, so next part is Euclidean distance. So Euclidean distance is basically another way to measure distance. And essentially it's Pythagorean theorem. So just kind of show of hands, who remembers about Pythagorean theorem? Yeah, I'm sure all your math teachers probably try to like drill that in your brain as much as possible. But if you remember, a squared plus b squared equals c squared, right? Essentially that's what we're doing. The c squared is the distance. So just know in this case that we're talking about Euclidean distance. That doesn't mean you just have, you know, x1 and y1. You could also have like 3 dimensions where it's like x, y, and z. So essentially we're measuring how as the crow flies. Okay. So the basic formula here is you take the square root after summing up everything, all the distances in that direction. So like imagine like x1 minus x2 squared, and then add up, you know, y1 minus y2 squared, and then add up z1 minus z2 squared in whatever dimensions you have, right? And then take all that together and take the square root of it. Okay. Makes sense so far? Cool. And so note that this is also called, like, we might call it Euclidean distance, but you can also call it the L2 norm. So L1 norm was basically using that one dimension, which is absolute value. L2 norm is using Euclidean distance, right? Second dimension, and we'll talk about what LK norm, I guess, is. But essentially you can imagine like this being the L2 norm. Okay, cool. So again, one way you can kind of imagine this too, like, let's see here. Actually, some good analogies to this too. Like we've actually used Manhattan distance in Euclidean distance already. So one is basically the mean absolute error, or MAE. So the mean absolute error basically is just saying, you know, how far are you from the points, if you remember linear regression. But what's the other option we have if we don't use mean absolute error? What's usually just talking about like the 3 letters. Also starts with letter M. What's that?
Mean squared error?
Mean squared error, good, MSE. And MSE basically is using the Euclidean distance, or we also call it the L2 norm. Okay, so the way we'd actually code this then is actually very, very similar. So note that I use the same points where I use 2, 3, 5, and 1 minus 1, 3. So we should still, remember Manhattan distance was distance of 7. Based on like what you guys know of, like, if you look at this kind of diagram here, the red versus the green, which is the diagonal here, which one's shorter?
The green.
The green, good. Good, you guys can use like distance and stuff like that. I'm sure you guys all got that. All right, so note that basically the Euclidean distance, right, the L2 norm is actually going to be smaller, right, than the L1 distance. So we should expect this to be slightly smaller than 7, okay? So we run this guy right here. We take the differences again, a minus b, right? And because there's a numpy array, we can do them all at once. So these are all the differences between 2 and 1, 3 minus 1, and 5 and 3, okay? Then what we do here, we square it. So note that in this case, I just multiply them together, but you could do something like np.power, for example, to raise it to the power. But in this case, I just squared them. In this case, this will multiply 1 times 1, 4 times 4, 2 times 2. So we get 1, 16, and 4, okay? And then I put basically the sum, np.sum. I'm squaring up all these parts. So we should get 17 plus 4 is 21, okay? Cool. And then the final step is, now that we added them all together, we take the square root, right? And the square root of that is, I don't know, something less than, what's 14, 5, less than 5. So let's say 4.4? 4.5 is 8. Okay. Anyone else know that? No, of course not. Why would you? So anyway, you can see here it's going to be smaller than Manhattan distance. Okay. And these are the 2 most common ones, right? Any other questions, or any questions about how we went through this, or how it relates to the Manhattan distance that we just saw?
We will either use one or the other, depending on.
That's right. So one thing to note is that, like, we talked about MAE and MSE, so mean absolute error and mean squared error. That's basically the difference between the L1 norm and the L2 norm. Is that, if you remember, one of the reasons why we used MSE, mean squared error, which is this guy right here, right, is that we are actually punishing very large values. So if the value is further away, it basically is affected more. And that comes from the fact that we're squaring the values. So this essentially turns out most of the time we'll use Euclidean and we want to punish larger values. But it turns out with higher dimensionality, which we'll kind of mention a little bit in K nearest neighbors, if you have many, many dimensions, so you can imagine not having X, Y, and Z, but you could have X, Y, Z, W, I don't know, U, V, T, or whatever dimensions you have, right? If you have like 24 different dimensions, this actually tends to perform not as well. So we actually need to use other things. One thing you might actually use is something we'll call the Minkowski distance. So we'll talk about what that is. Basically, it's a generalized of what we just saw. Or you might use something called cosine similarity, which I'll mention briefly, but we won't go into full detail. But yeah, essentially it's just kind of like what calls for the right situation. For the most part, you can probably rely on Euclidean distance. And honestly, if you don't need to do Euclidean distance, you probably will do something like cosine similarity. There are cases where you can use Minkowski, which I'll talk about in a second. Basically, you want to punish larger values a lot. So you basically are want to punish really large outliers. Okay, cool. Good question though. All right, anything else? Sounding pretty good so far? Okay, thumbs up if we're all following along. Cool, awesome. Simple maths, right? Okay, so now, like every good mathematician loves to do, is we're going to generalize this to basically any kind of like power. So Minkowski distance here, note that basically is used in like what I call like a normed vector space. Basically, something's already normalized in a vector space of multiple dimensions. And basically these two, Euclidean distance and Manhattan distance, those two are specialized forms of Minkowski distance. So we can also call this as like an LK norm. So basically, if I had the L1 norm, L2 norm, everything else is LK, and K could basically be whatever number you want. So what this looks like is this guy. So in this case, using the letter C, that's usually the parameter that we use. But you can see here, basically take the absolute value, right? And then raise it to the power of C. The reason why we take the absolute value is basically, if you raise it to the power of 3, you want to avoid that extra negative. So essentially, we're just taking it, making it positive, raise it to the power, and then taking the whatever root, like the cth root of whatever you're looking at. So if you imagine C equals 3, this would be absolute value, A minus K, or AK minus BK, which is basically each dimension, raised to the power of 3, and then add them all together, and then take one, the third root, so the cube root of this distance. But you can also do that with 2. And note if you put 2 in here, that is literally the Euclidean distance. Or if you put 1 in here, that's literally the Manhattan distance. Okay, makes sense? Cool. So just kind of quickly looking at this difference right here, I just defined a little function. So note that I split these up to make it a little bit easier. Note that you could put these all together in one function. So this way, you saw that I split these up. It's just a little bit easier for us to read, but you could put them all together. But you can see here, I take the absolute distance right here. So that's always true. Then I basically raise it to the power of C. So note that if I put 2 here, this would basically be the same thing as Euclidean. And then at the very end, I'm sorry, not the very end, we sum up all those distances together. And then at the very end, to find the final distance, we actually take the cth root. So you can imagine the second root or the square root would be this Euclidean distance. Okay, cool. So just to kind of show this what's in practice, I'll go ahead and have our little vectors again, right? So same old vectors. And so now if I put 1 here, this should give us 7, which is what we saw before. We get 7, right? If I put this as 2, we should get 4.58. Yeah. And then note if I put something like I put 5 here, this 5 basically will get smaller and smaller. Essentially, it's punishing those ones that are really far away, so they don't count it. It really cares about the ones that are close together. So basically, this number will get smaller and smaller. I could put 15 here if I wanted to, and note that it just gets smaller and smaller and smaller. Okay, cool. Any questions?
Looks like this just limits towards 4 rather than get smaller and smaller and smaller, right?
That's right, yeah. So it does technically get smaller and smaller and smaller. Basically, if you, what's it called? If you take this off to infinity, it takes the maximum distance. So you can see the maximum distance between each point is 2 and 1. Oh, sorry, 2 and 1 is 1. This is 4, and this is the distance of 2. It takes the maximum distance. So you can see that basically the maximum distance is 4. So eventually if I did like, well, it overflowed, so I made a mistake. That's a computer. But like if I actually went on this part, it would keep going closer and closer to 4, which is the maximum distance from here. Make sense? Note that just to kind of prove it, is like if I go ahead and write this as, let's say, 10, that's now the maximum of 7. So note that this will basically approach 7. Cool. Yeah, but it will limit up. Note that like when I put like 105, it's overflowing, so it doesn't know what to do. So it's kind of messing up. So it's not optimized, but you can kind of see, let's see how far I can go. And I can't go that far. That's okay. Okay. Good observation though.
Victor, will you restate what C represents here? I think I missed that.
Yeah, C is kind of like this hyperparameter. So it's not really like any like thing, how do I say this? It's not like really like any firm thing in the sense of like dimension or anything like that. It's more like saying how much are you willing to punish extreme values. So yeah.
Okay, thanks.
Mm-hmm. Cool. Yeah, it's a little abstract at this point. I think the first two are a little bit easier, and then once it gets past that point, you're just like, what's going on? They're essentially just another way to measure distance or how close something is to each other. Cool. But in practice, you tend to just use Euclidean, just so you know.
Is there a convention for how far you go with C? Like how much it's like too much punishment or like the outliers?
That's a good thing. I'm sure someone has written like a mathematical paper saying, you know, what thing to use in this sense. But in practice, what I see are two things. Essentially, you use Euclidean distance. You use Manhattan distance if you really don't want to punish from really far distances. Or you just use cosine similarity. So the two most common ones are probably like Euclidean distance or cosine similarity. Hopefully that kind of makes sense. But sometimes you might see up to, I think the highest I've really seen in practice is like maybe a 5, where they really wanted to punish high values. Past 5, I don't even know if there's a real technical reason why you would use it. Okay, good questions though. Okay, so all of this was just basically learning how to measure how far things are. Yay, so now you guys know how far things are, I guess, which is actually a really important part of our k-nearest neighbors. Okay, so I'll go ahead and move on to that part. So k-nearest neighbors, and that's the actual algorithm. So that whole part of distance, I wanted to take it nice and slow to make sure you guys understood, you know, how we're going to use like our distance. And once we understand how far different points are from each other, we can actually do our algorithm. So k-nearest neighbors is a classification supervised learning. So note that it's not regression. We're basically just saying, is it in group A, is it in group B, or is it in group C? Okay. And note that it's a supervised learning algorithm, which Andrew said before, supervised learning means that we already have examples of what things are labeled as. So if we know it, we already have some examples of, oh, this is a label A, this is a label B, this is a label C. Okay, so a quick summary before we dive into like the whole workings of it is essentially we have this green point here, this green circle, and I think this actually took this from data camp right here, just so you guys know. But and there's a good tutorial. I think the curriculum actually points to this one. But this green point here is our mystery point, and we're like, is this a triangle or is it a square? That's essentially what we want to determine. And so basically we use our already labeled points. So this blue squares and these red triangles are already like defined. Like we already know these are red triangles. We know these are blue squares, and they're plotted along some feature set. Basically this could be 2 dimensions, 3 dimensions, 4 dimensions, doesn't matter, right? And the idea here is like, okay, we see in this vector space that the green circle, it sits right here. Is it supposed to be labeled as a red triangle or is it a blue square? And essentially that's what k-nearest neighbors kind of tries to define. So kind of walking through a little bit of like how this algorithm works. We have a mystery point right here. In this case, it's a little question mark. You can see we have our reds over here, our little stars, and our triangles over here, class A and class B. And we say, okay, is this supposed to be class A or class B? And then what we do, we say, okay, how far is this question mark away from every point? So essentially we say, okay, from this question mark, how far is it from this point? How's it far from this point, this point, this point? And we can actually do this for all the different points, okay? And then from that thing, we say, okay, then what we do is we define the algorithm and say, okay, we're only gonna look at the 3 nearest neighbors, hence k nearest neighbors. So you can say whatever k, you wanna say look at the first 3, you wanna look at the first 5, you only wanna look at the first 1, that's what your k defines. And that's what the circle represents. And this circle basically says, all right, your 3 most nearest neighbors Okay, looking at those ones, which one is the most, which is the most popular one? So you can see here is that there's two triangles and one star. That means basically that it's like, okay, within k equals 3, so it's 3 nearest neighbors, that means it's most likely going to be a triangle since its most nearest neighbors are triangles. Okay, so you can see in this little graphic above, this kind of shows a good example, is that it really depends on what the k is. So you can see here in this solid circle right here, the green circle would be labeled as what? Triangle or square? I like this. Yeah, triangle, right? And I see Tara started doing that too. I like this. This is cool. I'll vote for square, vote for triangle. All right, and then if we had the dashed lines here, okay, so this is k equals 5 actually, so 5 nearest neighbors. I'm sorry. Yeah, 5 nearest neighbors. What would this circle be if we're counting these 5 nearest ones? Yeah, good. That's square. I do feel like sometimes I'm like Blue's Clues, right? It's like, is it a square or a triangle? But yeah, it would be basically based on this. So you can notice that it depends on what you define as the nearest neighbors, right? Or how many nearest neighbors you talk about. But essentially what they do, they each have a vote, okay? So it turns out this is a relatively, like if you think about this is a relatively simple algorithm, right? You can basically define you have all the training data right here, and you say, okay, let me go ahead and see where all the points are, and then put a new point and say, all right, how far is this one point away from everything else? And then you can decide which it is. So note that basically this is something called lazy learning, which is really nice to kind of say, but lazy learning basically says there's not really a training phase. It's super quick. Basically, you have the data and then you just say, all right, figure out what this new point is. And it's super fast to kind of, super quick just kind of figure this out. It's also easy to interpret. It's like, how do you know this point is green or like a triangle or a square or whatever you're looking at, whatever class it is? You just say, because it's the ones that have the most, the nearest ones near it. The most nearest to it is what it is. So it's kind of easy to kind of understand what's going on here, okay? Some disadvantages. Anyone got to guess what a disadvantage might be? And these are a little more subtle, I think, but anyone got to take a stab at it?
I guess it's easy to get it wrong. Like there's a high error.
Yeah, so I think maybe like when you say easy to get it wrong, it can be ambiguous, right? Because if you saw like up here, it's like if you use k equals 3, you're like, hey, like clearly it's a red triangle. But if you use k equals 5, you're like all of a sudden have, oh, it could be a blue square. And that's kind of like the uncertainty in it by itself. Good. Anything else you guys wanted to guess at disadvantages? So one is like k is being kind of ambiguous, right? You kind of define what you say k is. All right. Some other ones, kind of, it's a little subtle, is that in order for you to use this model, you have to keep all of the training data in memory. So if you have 100,000 data points, every time you want to know one data point is like, is it supposed to be class A or class B? You have to use all 100,000, right? There's not a way for you to know ahead of time which things are actually nearby, right? You have to basically calculate all the distances and then only count the ones that are close by. It's not robust. And what I mean by that is it doesn't generalize well, which basically means it's like, you can imagine like, if you get new data points, like if you're to have something beyond your training set. So for example, if I get a point over here, maybe this should actually be like, if you imagine if I drew out kind of this distance, like maybe all the red triangles, all the red stars end up only being like over here. And then the rest of it is a bunch of green triangles. If I put a point right here, okay, it's never seen anything. So it's only going to use whatever training is. So it's not super robust. It basically can't figure out like what is the best optimal thing. It could be the cuts right here. It could be the cuts right here. It could be in a lot of different ways. So it's not very robust. This also goes with soft boundaries are troublesome. So imagine if like maybe on the edge here, like if there's a very strict line like this, it's pretty easy. Like, oh, everything off to the left over here is a triangle or a star. Everything to the right over here is a triangle. But if it's something just some mixing, so for example, if we get some like stars over on this side, it's a little hard to tell like what is this part in between here. And there's not a really clear way to do this without doing something a little more advanced and stuff like that. So we basically get these soft boundaries, which again comes down to a little bit of something called decursive dimensionality. And basically it means that things are more separable in higher dimensions. There's a way to kind of prevent this, essentially kind of like the best way I kind of explain this is that like things that are higher dimension tend to be further away. So when you're in a higher dimensional, let's say a 10th dimensional space, things that are quote unquote, like most things around you are actually very, very far away, which makes it really difficult. Like you can see here is that this point right here in 2 dimensions, it's really far. In 3 dimensions, it gets even lonelier and lonelier. Essentially you have more volume to how much space you have. So essentially with higher dimensions, which could be a lot, like you saw in some of your so your learning models, stuff like that, you might have many, many, many features, right? That means you have high dimensionality. So what you can do then is use something called PCA, which we'll learn later on. Basically, it's principal component analysis to kind of reduce the number of dimensions. Another thing you can do, instead of using the distance, you can do something called cosine similarity. And basically, cosine similarity basically says how far the vectors are angled to each other. So instead of measuring, like if you imagine, I'm going to just draw it in 2 dimensions here. If you imagine if I have 2 dimensions here and I have this point and this point over here, we could do something like, let's say, Euclidean distance. But another way to do it is say, okay, let's draw an arrow from here to here and an arrow from here to here. And you say, how big is this angle? And essentially that's what cosine similarity says. The smaller the angle, the closer you are together. And what's nice is that this is pretty consistent regardless of dimension. So you can imagine essentially you always have a 2-dimensional plane that will fit those 2 points on there. So higher dimensions, you will tend to see cosine similarity. So that's why I said like technically you can use like higher Minkowski spaces, but in reality, you probably will just use cosine similarity. Okay, makes sense? Any questions on these advantages or disadvantages for k-nearest neighbors? Cool, yeah, so based on these advantages, what I would say is that if you have a relatively small data set, like training set, you can probably use this pretty easily, right? You can keep that in your thing, but just know there's these advantages, one being that it's not very robust and if they have soft boundaries. So you want to make sure that it makes sense that there should be a firm boundary. If it's a little fuzzy, then maybe k-nearest neighbors is not the best. And this is kind of our first kind of exposure to like a machine learning. There's a bunch of other ones we can do as well. Okay, cool. So next part basically kind of suggested from here is like, how do you determine which is the best, k? What's the best number to use for k, right? So we saw 3 and 5. So anyone got a guess what you can do? And I'm gonna tell you, it's pretty simple actually, when you think about what to do. So imagine we have a bunch of training data and we have some like points that we want to test out and see if they're right or not. So we actually know what they are, but we're not using it to validate the model. What's a simple way you can kind of check what the best k is to do?
Could you use the whole length of the data?
Whole, you mean like
how many
like,
data points you have?
It won't necessarily tell you what k to use. It's even simpler than that.
Yeah, I was saying like if k could be,
or
no, it's too large.
Yeah, I guess that's a good point. If you have like 100 points, you wouldn't want k to be 100 because you'll always get 100, right? It'll just be whoever's the most in there. So I guess that is a good point. If you do have a lot of them, you want to make sure it's lower than that. But usually that's not too much of a problem. One simplest way is basically you just try it out. You say, because it's super fast, right? Lazy learning, no training phase, it's relatively fast. You just say, all right, let me just try it with a bunch of different k's. K equals 1, k equals 2, k equals 3, k equals 4. And you see based on your green circles, so you have many green circles, and say, how well did it perform? And whatever k did the best on it, you say, that's the k I use. Essentially, that's what you would do. You just try many, many different examples of this. So essentially, here's one kind of curriculum. Basically what you do, you say, all right, let me try k equals 1. You might try k equals 3. Usually when I see this in practice, you tend to do like powers. So you like k equals 1, 3, 5, 10, 17, something a little bit spaced out. And that way you can kind of get an idea of how well it performs. And so also from the curriculum, you can see here 1 through 20, which tends to be pretty typical. Usually you won't use more than 20 just because you get the idea after that point. But you can see here with very small number of Ks, this represents like how bad the error was. So you can see here is that higher errors are bad. And as we get more and more K, you get smaller and smaller. there's a certain point where basically you'll tend to get more error as you get too large. So this is kind of being a little optimistic. Usually what I see is that it'll either do something along of like, it'll kind of drop off and either flatline. So it'll go like this way, which means basically, so, oh, smaller k is probably fine. You don't need more complexity than you need. The other one is that you'll tend to see kind of like this going back up. And the reason why it goes back up is, like I said, like if you included every point, you're just saying what's the most common point in there. So the error will get worse and worse kind of deal. So essentially what you'd find is that since this was relatively quick, you can just do like, okay, let me try like, you know, k equals like 2, k equals 5, k equals like, you know, 8, 12, 16, and just 20 for good measure. And you go off of this part and you might see this pattern. If you're still not sure, you can then investigate a little bit closer, like say, oh, okay, it's somewhere around here. Let me try 5, 6, 7, 8. And because it's relatively quick, it's pretty simple to like actually run on your machine and everything. Okay. Make sense? Cool. Any questions so far? Okay. All right, and so one last part is overfitting, underfitting, and we'll talk about this all the time, but I'll just kind of briefly mention it because the curriculum shows it. So again, this is the picture from curriculum, is that what you want to see basically is that there's a certain point where this is not a complex enough model, essentially. So we'll get a lot of not overfitting, underfitting. So we have some underfitting here and then a drop down. And then what happens, we'll get like this nice Goldilocks kind of like just the right, you know, K. And then we'll start overfitting basically, where we'll start getting a too complex model. And you can see here in this example, it's getting way too complex. The same thing kind of happens where you basically get more and more errors. So your sweet point will always like, you'll tend to get these graphs where if you imagine this is the complexity of the model. So this is like any model, not just K nearest neighbors. So this is the complexity goes up. This is like the error. What you'll tend to find is that the really simple ones is not very good. So your error will be relatively high, and then it'll drop down a little bit. And then it gets complex, more and complex, and then gets so complex that it doesn't do a good job anymore. And that's where basically you get into overfitting. And essentially what you want is just the right amount of complexity, which is right here. Okay, cool. Note that this is representative of training the model and then actually proceeding with doing something like validation sets, right? Or we call it test set, but really should be called validation. It's basically data it hasn't seen yet to train. So what will happen in practice if you're training with more complexity, and we'll see this more, this won't be the last time we'll talk about this, but as you get more and more complex with your training set, you will almost always see the more complex it is, the better the error, right? So like you can get super, super complex and your error will be like nearly zero, if not perfectly zero. But what will happen with your validation set, or sometimes we call it our test set here, it'll kind of go down, 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 and then it'll peak back up. So that's because we overfit on the training stuff and it's no longer fitting to it in general. Okay, so we'll see this graph over and over again. Cool. And note this is called an elbow plot. All right, cool. Any questions on these parts? Sound pretty good so far? Okay. So we have just enough time to basically just give you an example of what this looks like when you actually code it. So note that I'm going to use sklearn, and that's pretty much what we're going to use for like the rest of the module. If not kind of like, it's kind of like the standard of what's going on. So scikit-learn has a lot of these machine learning algorithms built in. I think the curriculum even talks about like, you know, you can make this from scratch, but sklearn just tends to be so much more optimized. Basically, there are people who are using it all the time that it's just might as well just use this. So just kind of know that's what I'm doing. In this case, I'm just getting the data set ready. I'm getting stuff to be able to plot it. So in this case, I think the data set is something like maybe, I can't remember, maybe a couple hundred. I can't remember how many data points. But I just kind of showed you what this data set is. And you can see here the different classes, the gray, the orange, and the red. So you can kind of see is that there seems to be over here, there'd be over here, and then over here. So you can imagine like, and this is 3 dimensions, 3 different attributes. I only did 3 features because it's easy to see this way. But you can imagine if I took a new point and put it over here, you'd probably think it's gray. If I put a point over here, which is orange, probably orange. If I put a point right here, it'd probably be red. If I put a point in between here, and it's not super clear what it should be. And you'll notice that basically it's kind of dependent on like how close it is. But that's kind of the, what's it called? The disadvantage, right, for k nearest neighbor. But the idea here is like seeing how far, if it's further away, maybe it determines as orange, maybe it determines as red, depends what it's near. Okay, so we'll actually use from sklearn, has a built-in class called kneighbors classifier. So we'll use this guy. We're going to use k equals 3, so n neighbors is equal to 3. Note that I'm using the metric Euclidean. If you look at this part, you'd notice that the metric by default is Minkowski, and I think actually it's using Euclidean by default by p equals 2. So you could actually change this out and everything like that. And this neighbors is 5 in this case. So you can change this part around and everything. I'll let you kind of check out the document as you guys need. Okay, but I basically say, okay, go ahead and fit it. And basically I have all this example of, let's call it our X and our Y. I should make sure I actually have, I have a test set differently. Okay, so this is training it with all the data. So note that I don't use any validation. I'm not using validation or test set, right? So it basically figured out what this k nearest neighbor is. As this neighbor, it uses the fit of using those positions, and these are the classes. And now I can say, okay, let's check out these different points. So these are just random points that I created, just saying, oh, if I put a different points in different parts of the graph, what would it be defined as? And it can make a prediction. So it basically determines that this point should be 2, this point should be labeled 2. You'll see that this label is 0, and this one's label 1, right? So you can kind of see that's the order that's going in, okay? So that's at least what the model thinks it is. What that really is, who really knows? I just kind of made it up just so you guys can see a little bit what this looks like. Now this might be kind of tough to see, like, well, what exactly does this look like? So we can actually go ahead and print this, or not print this, but plot this out. So you can see here is that these red points, or these big circles, are the points I defined way up here. And these colors right here are, the colors that you see on this are represented from this, you know, predicted label. So you can see here is that the one over here, as you expected, ones that are way up high over here, these are kind of red, these tend to be gray, these tend to be orange. Note that I have one that's over here off the side, and it's still predicted to be orange, probably because there's probably, like, if I use k equals 3, there's probably more orange that are closer, even though I probably, if you think about this, it'd probably make more sense for it to be red, right? Okay, so note that kind of like this is some of the issues with like k nearest neighbors. Okay, cool. Does that make sense to everyone? Cool, I see some head nods, cool. And just to kind of show you a little bit, like this will probably get fixed if I have a higher, let's say if I use k equals, let's try 6. So you can see the labels changed, and you'll see that that one on the top might change actually, because there is some difference in here. And if I go ahead and print this out now, you can see here, now it's using more data points, so it's probably gonna get it more correct. Okay, cool. All right, you guys have any questions then, or okay. Thumbs up sound pretty good. I think I saw most head nods and everything. Cool, cool. All right, so I guess I'll go ahead and stop recording here. Sounds good.